we are going to see a beautiful proof of beta gamma function using convolution and Laplace transform. But before we begin, it's important to know what convolution is actually. So let's say we have two functions f of t and g of t. Now if we are finding the convolution of these two functions, the convolution is defined as integral from 0 to t of f of x g of t minus x dx. Basically, while x is going from 0 to t, if you are integrating f of x and g of t minus x dx from 0 to t, that will give us the convolution of f and g. Now the definition has a beautiful part. Basically, if we try to take the Laplace transform of f convolution with g, this will be equal to Laplace transform of f and Laplace transform of g. And so this can be found out using the definition. You can use the definition and make some manipulations. I will upload a video or link a video over here that proves that Laplace transform of a convolution is actually equals to product. This is normal product of Laplace transform of each function. And so we have this property. Now we will use this property in the convolution and make some manipulations. And then we will derive this formula. So first of all, let me write the convolution thing. F convolution with g of t is actually equals to integral from 0 to t of f of x g of t minus x dx. So now we will use convolution and use the property of Laplace transforms, make some manipulations and derive this formula. Now let us say our f of t is t to the power m minus 1 and g of t is t to the power n minus 1. Now let's say this holds true, and now if this holds true, I mean if we just assume this not holds true, if we just assume this, we will have f convolution with g. Let me basically write the functions itself. T to the power m minus 1 convolution with t to the power n minus 1. This will be equals to integral from 0 to t, and then the function f of x is x to the power m minus 1, and over here we will have t minus x to the power n minus 1 dx. And now this can be written as, now let us take both the Laplace transform and Laplace inverse transform, because they cancel each other out, so we can write this. Now this will be Laplace inverse transform. We can take Laplace transform of individual terms. First of all, Laplace transform to the power m minus 1 is gamma m by s to the power m, and then Laplace transform of the other function will be gamma n by s to the power n. And this is actually equals to integral from 0 to t of x to the power m minus 1 t minus x to the power n minus 1 dx. Now after this, now we can first of all add these two. I mean by addition, I don't really mean addition, I mean for the denominator we can add. In denominator we have s to the power m plus n, and we have integral from 0 to 2 x to the power m minus 1 t minus x to the power n minus 1 dx. Now after this we can take gamma m and gamma n out, and now we will introduce gamma m plus 1 over here in denominator, and since it's just a constant, we can also take inside the Laplace inverse transform, and this is because it makes the standard form where we can take the Laplace inverse transform. Yeah, integral from 0 to 2 x to the power m minus 1 t minus x to the power n minus 1 dx. Yeah. Now this Laplace inverse transform of the function will just be, sorry, this is just gamma n by gamma m plus 1, and the Laplace inverse transform will just be t to the power m plus n and minus 1. Yeah, so is it? Yeah, okay. So now for the Laplace inverse transform is this function, and over here it's 0 to t x to the power m minus 1 t minus x to the power n minus 1 dx. Now this is just a generalization of our beta gamma function. Yeah, and now the special case is when t is equals to 1. When t is equals to 1, 1 to the power m plus n minus 1 is just 1. Yeah, so in the left side we will have the well-known functions, and 1 to the power something is just 1 is equals to, now integral from 0 to 1 1 to the, sorry, in x to the power m minus 1 1 minus x to the power n minus 1 dx. Now this is just the beta function of m and n, and so we have proved the relation. Yeah, and this was the proof of beta gamma function using convolution integral. And yeah, I hope you did really enjoy the video. Yeah, I hope you enjoyed this, and hope you will have a great time ahead. Yeah, thanks for watching, and look forward to seeing you in the upcoming videos.